Hi guys, this is Dr. Momsilovich with your lecture 14.1 on global ecosystems. Within the Earth's global ecosystem, it can be broken down into 4 different compartments. Those compartments all interact with each other, and they are the atmosphere, which is the air part of our Earth, the lithosphere, which is the land or the terrestrial part of the Earth, the hydrosphere, which is all of the water on the planet, and then the biosphere, which we've already covered, is all of the things that are living on the planet. So 3 of the compartments are abiotic. The biosphere is biotic, meaning living. So the atmosphere, the lithosphere, and the hydrosphere are all abiotic compartments of the Earth. Those abiotic compartments follow the rules of chemistry, physics, and geology, and we're going to go into a little bit more detail on some of those processes within each. Let's start with the hydrosphere. So this is the part of the planet that is water. We call Earth the blue planet because it is the only planet, at least within our solar system, that has liquid water on its surface. The hydrosphere is all of the water on our planet. Of that water, 97.5% of it is salt water and only 2.5% is fresh water. So these graphs on the bottom of your screen give you a good indication of how much of the planet is covered in salt water compared to fresh water. So only 2.5% of that water on the Earth is fresh. Out of that 2.5%, 0.3% of it is in lakes and rivers, so not much of it. About 30 to 31% is in groundwater, which is water that's beneath the rock on the Earth's surface. And the other 68 to 69% of it is actually locked in glaciers. So most of our fresh water on the planet is locked in places that we cannot easily access. Water on the planet goes through the water cycle or the hydrologic cycle. This is a cycle that is powered by solar energy, where the sun heats up the oceans and it causes water to evaporate, and that starts this water cycle. So you have water in oceans and lakes and rivers and things like that. The sun heats that water up and it causes it to gain energy, which allows it to evaporate. As it evaporates, it gets up into the sky and it cools and it condenses into clouds. Over time, that condensation will again fall back to the Earth in the form of precipitation. That precipitation can be snow or rain or sleet or hail or whatever it is. It gets back down to the surface of the Earth. Some of it can freeze depending on where it falls and become ice. Some of it will go back into lakes and streams and the oceans. Some of it gets down into groundwater, but either way, it's back onto the surface of the Earth once it has precipitated, and then it can go back through that process. So all of the water on the planet is constantly being recycled between the ground and up into the atmosphere and then back down again. So while we're talking about water going up into the atmosphere, let's talk a little bit more about the composition of the atmosphere. So the Earth's atmosphere is a thin layer of gas, and it reaches up to about 10,000 kilometers away from the surface of the Earth. So you can think of the atmosphere as a larger sphere that circles the Earth, and it extends from the surface of the Earth out to about 10,000 kilometers away from the surface. The atmosphere is broken down into several different layers. The 2 that are the most important to us are the troposphere and the stratosphere. The troposphere is where most of our weather occurs, and it's where 75% of the molecules in the atmosphere are contained. So most of the molecules that we have in our atmosphere occur in the troposphere. And this is the layer of the atmosphere that we actually live on. The troposphere is the part of the atmosphere that is in direct contact with the Earth. So it's the layer that goes from from Earth's surface out to about 17 to 18 kilometers away from the Earth's surface at the equator, and out to about 7 to 8 kilometers away from the Earth's surface at the poles. So depending on your geography, the depth of the troposphere is going to be different. The next layer that's important is the stratosphere. So the stratosphere contains the ozone layer, which is important because it protects us against solar radiation. So in a little bit, we're going to talk more about the greenhouse effect, and the ozone layer within the stratosphere is an important part of that. The ozone layer actually keeps a lot of harmful UV radiation from the sun from reaching the Earth's surface. So we rely on that ozone layer to keep us protected from UV radiation that would be able to cause genetic issues and other things to happen if that radiation were to reach the surface of the Earth. The ozone is also important because it traps heat energy within the Earth to keep us warm. So the composition of the air on Earth is mostly made of nitrogen gas, which is an inert gas. So 78% of the air that you breathe is actually nitrogen. 21% of the air that you breathe is oxygen. About 0.9% is argon, which is also an inert gas. And then about 0.4% of the gas that you breathe in is carbon dioxide. So as you breathe out, you're expelling carbon dioxide. Anything on the planet that's doing respiration is creating carbon dioxide. And essentially, one of the main ways that we get carbon dioxide out of our air is through photosynthesis. So plants take in that CO2, do photosynthesis, release oxygen, but most of the air on the Earth is made out of nitrogen. In addition to the gases that normally occur within our atmosphere and the air that we breathe, there are other things that are there because of human activities like industry and farming and engine combustion and things like that. And those pollutants, those toxins, make up a small but important part of the air that we breathe. So as humans are doing all of these activities, you have anthropogenic, which means human-caused emissions from the Earth of carbon monoxide, carbon dioxide, sulfates, nitrogen oxides, things like that. Those are all things that are pollutants and are bad for the air and can also be greenhouse gases. Those things get moved around the planet by larger wind patterns that blow them from their source over to other places. And so you don't ever have just pollution happening in the place where the pollutant is being released. That pollution gets spread across the surface of the Earth through the processes of winds and things like that. Some pollutants stay in the troposphere, which is where humans live. Other things like CFCs, which are chlorofluorocarbons, this would be things like chlorine, bromine, and fluorine, are actually able to break up into the stratosphere. And those are harmful and dangerous because they are able to interact with the ozone molecules that are in the stratosphere and break those molecules down. So when we're talking about the ozone hole that occurs in parts of our atmosphere, that occurs because of human activities where certain pollutants that are released by humans are able to make it up into that second layer of the atmosphere and break down that incredibly important ozone layer. Other pollutants that occur down in the troposphere are ozone. So up in the stratosphere, it's beneficial. We need it there. But down in the In the troposphere, it's a pollutant that can cause issues with some crops can't grow in the presence of ozone. It causes lung issues in people. Other things like nitrous oxides and sulfur dioxide, those combine and make acid rain. And so within the atmosphere, we don't only have the gases that are important and are naturally occurring, we also have other things that are added to it because of human activities. Another important part of the atmosphere is weather and climate. So sometimes we use these terms interchangeably, but they actually do mean very different things. So weather is your short-term conditions. So this is something that can change over minutes to months. And it can be somewhat unpredictable. So you can have sudden rain showers. You can have one day that is 70 degrees and the next day it's 90 degrees, right? So that would be something that would be a weather-related phenomenon where, for this example, on this day that the screenshot was taken, it was a high of 99 degrees Fahrenheit in Mesa, Arizona. So we're talking about changes that happen daily or even weekly or monthly. So in Phoenix, in the month of August, it's sunny, it's hot, it's dry. Those are weather conditions. When you have a sudden onset of a monsoon, that would be weather because it is a daily or monthly change. Climate is a long-term pattern of weather in a particular area, and it consists of averages that last 30 years or more. So with climate, you're able to make predictions like how can you predict that Arizona will cool down in the month of November? Well, we can look back at averages for each day or each month from the past 30 years, and that data shows trends in any area's climate where during certain months the weather will change and cool down on average. Weather can be variable by day. So for example, right now the weather is about 10 degrees warmer than average. But in general, the climate in Arizona is that it's very hot in the summer months and it cools down in the winter months. It's dry, and that would be the climate of the Phoenix area. So while we're talking about weather and climate, we need to talk a little bit about climate change. So climate change is happening because of increases in greenhouse gases, which increase the greenhouse effect. So there is a natural greenhouse effect, which is good and normal, and it keeps the earth toasty and warm the way we want it to be. This happens when CO2 levels are at about 250 parts per million. What happens when we have excess CO2 levels is called an enhanced greenhouse effect, where this causes climate change and the earth overheating. This can occur when CO2 levels are at 350 parts per million or more. Currently, as of April 2020, so that was a few months ago, the CO2 levels in the atmosphere are at about 416 parts per million. So we're well above the threshold of when we would expect to have an enhanced greenhouse effect. The greenhouse effect works by trapping in the radiation from the sun to keep the planet warm. So the Earth's rays hit the Earth. They have to make their way through the layers of the atmosphere to get to the surface of the Earth. A lot of the harmful UV radiation gets filtered out by the ozone layer. The rest of it goes down to the surface of the Earth. Most of that radiation gets absorbed by the Earth's surface and warms up that surface. Some of it reflects back out into the atmosphere. When it goes back out towards the atmosphere, it runs into some of those greenhouse gases, which are good at trapping heat. So that energy from the sun that's reflected back out into the atmosphere gets stopped by those greenhouse gases, and keeps the heat into the planet and therefore warms up the surface even more. When we have normal levels of greenhouse gases like CO2 in the atmosphere, the Earth stays at a very constant temperature. The more of those greenhouse gases that are present in the atmosphere, the warmer the planet becomes, because you now have more molecules that are trapping heat that is trying to escape the Earth. So the more of these greenhouse gases that we emit out into the atmosphere, the warmer we're making our planet because of the chemical properties of those gases. Let's talk about the lithosphere now. So this is the compartment of the Earth where you have the terrestrial or land part of the planet. This is the crust and upper mantle of the Earth. The lithosphere is separated into tectonic plates which move on top of the mantle, which is a partly liquid magma layer underneath the crust. The movement of those plates determine where oceans and continents are. Mountain chains also arise when two plates collide, like the Himalayas, or near subduction zones like the Andes. So the tectonic plates that are on the top of the Earth are moving around, and we've seen videos of this in the past when we've talked about biogeography and things like that, that you have continents essentially floating around on top of the Earth, and that's because the continents sit on large tectonic plates, which are large chunks of Earth that float around on top of that mantle layer. As they move around, they either are running into other plates and colliding, or they're pulling apart and creating subduction zones. So one place where two plates are colliding with each other is the Himalayan mountains. And this is where the Indian plate is running into the Eurasian plate. In this instance, the Indian plate is moving constantly upwards north, further and further into the Eurasian plate. As it's doing that, those two plates are pushing together and the land pushes up further and further. So those plates are constantly pushing together, and they're constantly causing those mountains to get slightly taller year after year. So someone who climbs Mount Everest one year, it is climbing a mountain that's a couple centimeters taller than someone who climbed it the previous year, because those plates are constantly pushing together and pushing the mountains upwards. Subduction zones are places where those plates are pulling apart from each other. So this creates essentially a trench between the two plates. When you have an oceanic plate rubbing up or running into a continental plate, which is the part that's up above the sea level, that oceanic plate is denser than the continental plate, and so it will slide under the continental plate. And that can cause something like the Andes Mountains, which are formed by the dense oceanic crust pushing underneath the South American plate and pushing that land upwards as it's pushed back down into the mantle. Within the lithosphere, there's a few different cycles that are constantly going on. One of them is the nutrient cycle. So there are 92 naturally occurring elements on Earth. Organisms acquire those nutrients from their food. So in the graphic, those are the black arrows. Nutrients are constantly recycled and used over and over again. Energy from the sun is used and lost. However, nutrients are recycled. So this would be something like nitrogen that gets taken up by plants. Herbivores eat the plants and get the nitrogen into their tissues. Carnivores eat the herbivores and get that nitrogen from the herbivores. When any of those things die, decomposers break that material down and put those nutrients back down into the nutrient pool in the soil, where producers and autotrophs can then pull it back out from the soil, and the cycle continues again. So you're never creating new nutrients, it's always just being cycled over and over. Nutrients are stored in pools, which are where we have chemicals that are stored in a uniform manner, and this is measured in units of mass. For example, the largest carbon pool is the Earth's crust, which is sedimentary rock, and this stores 100 million gigatons of carbon in that sedimentary rock. Pools can either be sources or sinks, and these terms refer to pools that either generate large flux of these nutrients, so that would be a source, it's generating large flux of those nutrients back into cycles, or they store them or generate low flux, so places that are going to hold on to those nutrients and store them for long periods of time. Flux refers to a transformation from one pool to another in a nutrient cycle, and this is measured in units of mass over time. So for example, the flux between fossil fuel or geologic reservoirs of a nutrient and the atmosphere in 2018 was about 10.2 petagrams of carbon, which is about 1 billion metric tons. So you have carbon that is stored in reservoirs of fossil fuels. Through combustion, that carbon gets released out into a new pool, which is in the atmosphere instead of being in those reservoirs of that resource. The way that an element or a compound moves between living and non-living components of the earth is known as a biogeochemical cycle. Biotic reservoirs are things like producers and consumers and decomposers, and those cycles are very fast. The cycles can be anywhere from days to years. Abiotic reservoirs are things that occur within the atmosphere, the hydrosphere, and the lithosphere, and these are geologic processes where certain nutrients can be trapped within rocks or ice or within soil for years or millennia. And these are very slow processes of the turnover of those nutrients. Those can be sped up by human activities, which has been happening quite a bit. But in general, the abiotic reservoirs are considered to be very slow-moving processes, whereas the biotic reservoirs are very fast. Another important biogeochemical cycle is the nitrogen cycle. If you remember from earlier in this lecture, we said that most of the air that you breathe is made up of nitrogen gas. So most of the nitrogen is in the air. Plants need nitrogen to grow and do photosynthesis, and so it is a limiting resource. There are special bacteria that live in certain types of soil and in the root nodules of legumes, which we've talked about before. Those are things like peas and soybeans. They have rhizobium bacteria that live in their root nodules and are actually able to do nitrogen fixation, which is taking nitrogen out of the air and converting it into a form that can be taken up by plants. So those nitrogen fixing bacteria will pull nitrogen out of the air and convert it into other forms. Nitrogen goes through ammonification and nitrification, and through other processes makes it back up into the atmosphere and then continues back down. And so the nitrogen cycle is a constant cycle of pulling nitrogen out of the air, converting it into a form that plants can take up with their roots and use, and then through other processes it gets released back into the air and the process continues again. So like I said, nitrogen is a limiting resource for plants, meaning that plants need it to grow, but there's not always enough of it in in the soil for plants to be able to grow to their fullest potential. And so farmers will intentionally put nitrogen and phosphorus onto their plants through fertilization. Other nitrogen gets released because of other human activities like industry and things like that. And that can cause an issue which is called eutrophication. Eutrophication happens when you have too much nitrogen and phosphorus getting into a body of water, which allows the algae and other plant material to grow in abundance. Once that plant material dies, there is bacteria that come in and break down that dead organic material. Bacteria use oxygen because they're living, and when you have a lot of dead material that's being decomposed, that bacteria actually sucks most of the oxygen out of the water. That can kill fish and other things that live in the area. And so we end up with dead zones that occur in places where you have a lot of excess phosphorus and nitrogen from fertilizers, because you end up with that overgrowth of plants, and then the plants die, and you have microorganisms that come in to feed on the dead plant material, and that sucks the oxygen out of the water. So here's a little bit more detail on the nitrogen cycle. So remember that 78% of the atmosphere is inert nitrogen gas, or N2. Living organisms need nitrogen to make protein, but they can't use N2 gas directly. So there are two very important processes that have to occur that happen with the help of bacteria. Bacteria do nitrogen fixation, which is where nitrogen gas is converted to ammonia. Ammonia can be taken up directly by plants and assimilated into their tissues, and then that is consumed by herbivores and then carnivores, which assimilate them into their tissues to make protein. The other process is denitrification, where you have nitrate converted to N2 gas. So this would be during decomposition, where you have bacteria that are breaking down material and releasing nitrate back into the air as nitrogen gas. There are a couple of human impacts on nitrogen fixation that are causing an increase in this process. So farmers are planting more and more legumes, which are soy, peas, clover, things like that. And those have those special bacteria in their roots that perform nitrogen fixation. So we're constantly adding more of those plants to farm fields because it's good for the soil to have those organisms in there. But that leads to increased nitrogen fixation. Farmers are also using more and more synthetic fertilizers that are made using the Haber process, where you have an increase in nitrogen and phosphorus in those fertilizers, and that is another way that we're getting more and more of that nitrogen into soils. The sulfur cycle is another important nutrient cycle. The sulfur cycle has sulfur cycling between rocks and the biosphere. So sulfur is released from rocks through the process of weathering, and then it's assimilated by microbes and plants into their tissues. It then gets passed up through the food chain and assimilated by plants and animals and released when they decompose. However, currently, excess sulfur is being released into the atmosphere because of human activities. So coal-burning power plants release excess sulfur, as well as burning fossil fuels. When large quantities of nitrogen oxide or sulfur dioxide are released into the atmosphere, the gases are able to dissolve in water, forming acids. Acid rain occurs when the precipitation, so rain, sleet, or snow, is acidic. This is damaging to plants by affecting their ability to absorb nutrients, and affects aquatic animals like fish and amphibians by making their water more acidic. Next is the phosphorus cycle. The phosphorus cycle is unique because this cycle doesn't have a gaseous form. It only occurs in solid forms. So the phosphorus cycle begins when it rains and phosphates are removed from rocks because of weathering and erosion. Those get distributed throughout soil and water, and plants take up the phosphate ions that are in the soil. The phosphates then move from plants to animals when herbivores eat plants and carnivores eat herbivores. And then the phosphates that are absorbed into animal tissue eventually return to the soil either through excretion of urine and feces, or when final decomposition of plants and animals occurs after their death. Human impacts on this cycle are increased phosphorus in water systems. So mined phosphorus is used as an agricultural fertilizer. Fertilizer that is not absorbed by plants gets into groundwater and then into lakes and streams and rivers and eventually into the ocean, causing that eutrophication issue we talked about. And excess phosphates in wastewater, like feces and detergents, etc., also occur where you have the same process happening, where you get excess of phosphorus and nitrogen in the water and eutrophication can occur. The carbon cycle is a very important cycle for humans. This diagram shows the cycle of carbon between the atmosphere and other reservoirs of carbon. Black arrows are human activity, and gray arrows are natural cycling. So naturally, carbon is constantly being exchanged between the ocean and the air. So cooler water will actually hold more carbon than warmer water, and carbon is constantly being released and reabsorbed by the ocean. Carbon is released through respiration of plants and animals, as well as decaying matter. But it's that carbon, that CO2, is reabsorbed by plants for photosynthesis. So plants like forests and grasslands and things like that are big reservoirs for carbon, as well as the ocean, which holds on to a lot of carbon and absorbs it. Humans are increasing the production of atmospheric CO2 by burning fossil fuels, which produces CO2, as well as changing land use, so changing forest to cropland, and also just because of human activity destroying certain land and turning it into desert where it no longer has plants that are able to take that CO2 out of the air. So because of the continual excess release of CO2 from human activities, as well as the diminished ability of the planet to absorb that carbon into forests and other plants, we're increasing the amount of carbon that's in the atmosphere. So if we briefly go back to this image of the greenhouse effect, one of the greenhouse gases that's very important is CO2. So as we're releasing more and more CO2 out into the atmosphere, more and more of that heat that should be escaping the Earth is being trapped, and that is what is heating up our planet at a faster rate than is natural. The greenhouse gases that occur in the atmosphere are carbon dioxide, which is CO2, methane, nitrous oxide, and fluorinated gases. They all have what we call global warming potential, which means that they have the ability to warm up the planet. So in general, methane, nitrous oxide, and the fluorinated gases actually trap more heat per ton released. So they have higher global warming potential than carbon dioxide. However, we are generally more concerned about CO2 than any of these other gases because there is a lot more carbon dioxide and we release more of that than any of the other gases. So although methane, nitrous oxide, and fluorinated gases have a greater ability to warm up the planet, carbon dioxide is the gas that we focus on the most because it has a greater warming potential for the planet. CO2 emissions come from several different places. So the largest would be electricity and heat production. So this would be operating things like coal-fired power plants, also from agriculture and forestry and other land use that's causing CO2 emissions. Industry, transportation, which would be driving your car or flying in an airplane, that would be engine combustion. Buildings, other energy, things like that. And this is not just a localized problem, this is actually a global problem. So in 2014, the emissions of fossil fuel combustion and some other industrial processes, 30% of the CO2 emissions came from China. 15% of it actually came from the United States, 30% from other countries, and then others that have made this list are Japan, Russia, India, and the European Union. So if we look at the amount of emissions compared to the number of people that live in these countries, China has a billion or more people that live in that country. However, the United States have about 320 to 330 million people. So the United States is releasing a disproportionate amount of CO2 into the atmosphere compared to how many people. And so the United States is usually one of the biggest offenders in having excess CO2 emissions. So we have currently that enhanced greenhouse effect that we talked about, meaning that we're having more and more greenhouse gases being emitted into the atmosphere. This is causing global warming. That global warming results in climate change. So if no changes were happening, we were business as usual, the predicted warming is about 4 to 6 degrees Celsius by 2100. That's from the year 1700 to 2100. We would have 4 to 6 degrees Celsius change. That would be if we don't change anything about our current activities. We have already changed by gaining about 1 degree Celsius in temperature. Anything over 2 degrees Celsius is considered to have catastrophic effects. The last ice age had about -6 degrees Celsius, and Europe was completely covered in ice. So even though we say it's going to be 4 to 6 degrees Celsius, and it doesn't sound like a lot, that's actually a very large change in the temperature, and those large changes can have global disastrous effects for humans. So sometimes people who deny climate change ask, what is the potential long-term effects of climate change? And there are a number of things that could be very harmful to humans and every other living thing on the planet. So warming of the planet is causing melting of ice and rising sea levels. So a lot of water is trapped in the ice caps. And if that water melts and makes it into the oceans, there are areas around coastal parts of the world that are going to experience flooding. So not only are we going to have more water entering the oceans, but as water warms, it expands. And so we're talking about excess water as well as expanded water causing the rise in sea levels. We're also experiencing extreme weather patterns. So we're seeing more floods and droughts. We're seeing more and more intense hurricanes and things like that. Shifting rainfall patterns where rainfall is lessening in some areas and increasing in others. There's risks for human health. So as the planet warms, we're having more health issues. There's issues with tropical diseases and things like that that are carried by mosquitoes being able to move further north into areas that are heavily heavily lived in by humans. There's issues with changing agricultural yields. So as rain changes and temperatures, it affects the ability of plants to grow. We're seeing increased extinction rates. So the change in climate is happening faster than plants and animals are able to adapt to it. So we're seeing higher extinction rates. We're also seeing the movement of plant and animal ranges. So as areas are getting hotter, animals are able to move further north out of their normal ranges. So places like Florida are seeing more mosquitoes and other snakes and things that are moving out of the tropics and are able to live further north. Also, you're having plants that are no longer able to grow in the same areas because the weather conditions aren't the same. And that also causes issues because as you have plants and animals that are adapting to these new climate norms, you have insects and plants that should be active at the same time to allow pollination, and now their schedules are not matching up because the plants are blooming too early or the insects are coming out of their crypsis, which is an insect hibernation stage earlier, and plants and their pollinators are not matching up anymore in their timing. And all of these things are going to equal costs for society and for the economy as we have to come up with ways to combat these issues. As climate change, we are seeing a change in ecosystem services. So ecosystem services are benefits that people get from the ecosystems around them. Some of those services can be provisioning, so things like food and water, wood, fuel, things like that. It can be supporting people through nutrient cycling and soil formation and primary production. It can be regulating of the ecosystem, like climate regulation, flood regulation, disease prevention, and water purification. And it can also be cultural ecosystem service, like aesthetic and spiritual, educational, and recreational services that the ecosystem provides to people. And all of those things contribute to different aspects of human well-being. And as the climate is changing and it's changing the earth, we're seeing differences in those ecosystem services. So this chart shows the value per hectare per year of some of these different ecosystem types. So something like a desert has $0 of value for ecosystem services, but something like a coral reef has $352,000 per hectare per year value in ecosystem services, which is why it's important for the global economy that we do take care of our ecosystems. So ecosystem services are important because they contribute more than twice as much to human well-being as global GDP. The global loss of ecosystem services from 1997 to 2011 is about 20 trillion US dollars per year. For comparison, the US economy in 2020 is about 20 trillion US dollars. And so the way that ecosystem services are affecting human well-being is through recreation and through recycling of nutrients and cycling pollutants out and different ways. So as climate change is happening and as ecosystems are being deteriorated, we're seeing a decrease in GDP in most countries around the world through changes in those ecosystems.